On Monday. But I mean, your election. Um, so the way this is going to work, chapter 6 homework is due on the 16th. I mean, the 19th, sorry. The chapter 6 quiz is on the 17th. The chapter 5 quiz will be today after lecture. I'll keep the lecture short, so you have plenty of time for that. And the remaining days for lab will be for makeups. So if you're missing any labs, you can make them up starting next week. So the 19th, the 3rd, and the 10th are makeup days for labs. So let's talk about waves. Waves have some properties. All waves have a wavelength, which is the distance over which the wave repeats. For one complete wave, they have an amplitude, which is the maximum displacement of any part of the wave from the equilibrium position. And the energy transmitted by a wave is directly proportional to the amplitude squared. Waves are characterized by their frequency, which is the number of oscillations or cycles that occur during a given time. The unit used to describe frequency is a hertz. The hertz is 1/2 1 hertz is 1 cycle per second. And the period is the time it takes for a wave to travel a distance of 1 wavelength. And frequency and period are inversely related. So frequency is 1/period. Because speed is distance over time, speed is equal to wavelength times frequency, which means frequency equals speed over wavelength, and wavelength equals speed over frequency. For light, the speed is c, the speed of light. So electromagnetic waves consist of vibrating electric and magnetic fields that oscillate perpendicular to each other in the direction of the wave propagation. The field of energy radiates outwards at the speed of light, c, which is 3 times 10 to the 8th meters per second in a vacuum. And that's a good approximation of the speed of light in air as well. Because the speed of light in air is like, differs by less than 1%. It's a few thousandths. So this is an electromagnetic wave. We have the vibrating electric field, the vibrating magnetic field. The changing electric field creates the magnetic field. The changing magnetic field creates the electric field. And electromagnetic waves can be placed on a spectrum. The visible portion is what you see with a rainbow, because raindrops separate light out into a spectrum. The shortest wavelength waves, highest energy, are gamma rays, then X-rays, then ultraviolet, above violet, because they're higher energy than violet. Then infrared, below red, because they're lower energy than red. Then microwaves, then radio waves. This goes from highest frequency to lowest frequency, shortest wavelength to longest wavelength. Visible light has wavelengths between about 400 nanometers and 700 nanometers. But all of these are all the same thing, from radio waves to X-rays and gamma rays. They're all electromagnetic waves. They're just different energies or different wavelengths. Sound is the propagation of longitudinal waves through matter. pressure waves through matter. So solids, liquids, gases, all can transmit sound. So the vibration of a tuning fork, when it moves forward, will compress the air, and when it pulls back, will expand the air, stretch it out, rarefy it. It'll create a series of compressions and rarefactions. And so you'll see high pressure followed by low pressure followed by high pressure. And that continual vibration, this series of high and low pressure regions, will travel outwards, forming a longitudinal sound wave, which is what you have an eardrum that moves with that pressure, and you detect those vibrations. Loudness is a relative term, while intensity is quantitative, and it's a measure of the rate of energy transfer through a given area. Intensity can be measured in watts per square meter, and the threshold of hearing is around 10 to the minus 12 watts per square meter, and an intensity of about 1 watt per square meter is painful to the ear. And intensity will decrease with distance from the source. So if you have an intensity of, say, 1 watt per square meter at a distance of 1 meter, if you go to a distance of 10 meters, it will be 1/100th of that. It will be 1/100th of a watt per square meter. And it is also measured using the decibel scale, where each increase of 10 decibels involves increasing the intensity by a factor of 10. Any decrease of 10 decibels is divided by a factor of 10, because it's a logarithmic scale. So the Doppler effect is an effect that happens to sound or any wave when the source of the wave and whoever observing the wave are moving relative to each other. So as a moving sound source approaches the observer, the waves in front get bunched up and the waves behind get stretched out. So the observer will hear a higher pitch as the sound source approaches, and then a lower pitch, a longer wavelength as the source departs. And this happens for any wave. And the effect is proportional to the shift in wavelength or frequency is proportional to the fraction of the speed of the wave that the source is traveling. So it's a lot more evident at normal human speeds with sound, because we move a much bigger portion of the speed of sound than of the speed of light. But the same thing happens with light. And we use this to measure the speed of various astronomical objects, but it's also how like radar guns work in speed terms. So as you approach, the waves get bunched up in front and spread out behind. And here's an actual picture of that happening with water waves. You can see they're bunched up in front and spread out behind. So this vibrating source is moving. We're going to skip the video because we watched that, and I want to get through this relatively rapidly. Now, the Doppler effect does affect all kinds of waves: sound waves, water waves, electromagnetic waves. And in the electromagnetic wavelengths, the Doppler effect helps us determine the relative motion of astronomical bodies. So if something is moving towards us, the waves it emits will be shifted towards the blue. It turns out we can determine this from its spectrum because there are individual lines in the spectrum tied to the elements that make up the object, and those will shift. So a shift to shorter wavelength as the light source approaches the observer, and if it's moving away from us, it shifts to longer wavelength as it moves away from us. Red shift is much more common than blue shift because the universe is expanding, so almost everything is moving away from us. And these shifts in wavelength tell astronomers a great deal about relative movement in space. It's also understanding these Doppler shifts is actually how we figured out that the universe was expanding. And we're going to skip this one as well because we played that on Monday. Now, as a vehicle moves faster and faster, eventually it will go as fast as the waves it's creating. that will pile up waves in front of it. It will keep generating waves. They'll sit there in front of it because it's going just as fast as they are. And so the sound waves in front will get shorter and shorter until the vehicle reaches the speed of sound, approximately 750 miles per hour, depending on temperature. And as the jet approaches the speed of sound, the compressed sound waves in front and air build up and act as a barrier in front of the plane. You may have heard this this is the sound barrier that was originally broken by Chuck Yeager. And as you exceed the sound barrier, you form a high pressure shock wave in front, and this is known as a sonic boom. This is what happens when you're traveling faster than the sound waves you emit. They all move backwards, and you get this shock wave, shock cone that travels outwards. And you only hear this to the sides of, it's a cone emitted from the source. So like if you're shooting a rocket straight up and it goes supersonic, you don't hear the sonic boom because you're not in the right place here because it's going out sideways. And here's an animation showing the Doppler effect and shock waves. So here's a plane moving slower than the speed of sound. You can see the Doppler effect, compressed, shortened waves in front, spread out waves behind. So you hear a higher pitch here and a lower pitch here. Here is a plane moving exactly at the speed of sound. You can see the pileup of all the waves forming that sound barrier. It's actually very difficult to fly exactly at the speed of sound because you're constantly dealing with that sound barrier. You want to go faster or slower. And then here, we have faster than the speed of sound, and there's that shock wave, the sonic boom. So that was great. Now, one of the ways that you can create a sonic boom yourself is learn to crack a whip, because the crack of a whip is an actual sonic boom. It's the shock wave from the tip of the whip traveling faster than the speed of sound. So you send a wave pulse down a tapering whip. As a whip gets thinner, the wave on the string depends on the mass of the string per unit length. So because it gets thinner and tapers, it goes faster and faster as it goes towards the end. And that final crack is made by air rushing back into the area of reduced pressure created by the supersonic final flip of the whip's tip. And here is a video of that. So this is
Gets all of the wave kinematics on the macro scale, and then the Phantom can record the tip velocity and actually capture the formation of the shock wave.
So here you can actually see the wave. There is that sonic boom.
I'm not going to explain any of our preliminary conclusions, but at this point we're doing two types of analysis. Obviously how that wave propagates, but also the tip velocity of the whip. If you watch closely, it looks like the tip's getting pulled along behind that shock wave. This is super complicated and we're still analyzing this.
There it is without the cracker.
What we do know is that the popper isn't necessary. Dr. Konistras really wanted us to visualize the end of the whip with only a knot on it, and just look at how happy he was when his hypothesis was proven correct.
There you go. There you go. Yep. There you go.
So it's like this. For the first time in history, we have true XYZ data from the handle.
And you can watch the rest of that video on your own time if you want. It's a very interesting video, but it is also wrong. So that's where we got to on Monday. So let's continue from there. One of the things that can happen is that waves bounce off of stuff. So you can have a situation where a wave will bounce off of something and come back and add up with itself to create what's called a standing wave. A standing wave is a wave that looks like it's not moving. It's like what you'd see on a guitar string. And it arises from the interference of waves traveling in opposite directions. Basically, there's two waves, one going one way, the other going the other, that add up in such a way that you get a wave that looks like it's standing still and just moving up and down at specific points. So along a rope or a string, waves will travel back and forth. They can add up. They constructively interfere with each other, forming a combined standing waveform. In some places, they always cancel out. In some places, they always add together. And so you get something like this. We have a standing wave. We have some places that are fixed. These are called nodes. So here's one possible standing wave on this string. Here's another. Here's a third. You can see there are nodes at the ends. These are points that don't move. And on these shorter wavelength, higher frequency ones, there are nodes in the middle as well. So here we have one node in the middle. Here we have two nodes. And then there are antinodes. Antinodes are points of maximum up and downness. So here are the antinodes, here and here. And standing waves are formed only when the string is vibrated at certain frequencies. They're frequencies that correspond to wavelengths where a nice number of half waves fit into the length of the string. So here, this is half a wavelength, because if it was a full wavelength, you get the other half of this, that'd be, it goes up and then it goes down, it's bouncing back and forth. Here's a full wavelength. Here's 1.5. So it turns out there's a nice formula for this. For a standing wave where the ends are fixed, like on a string, the wavelength equals 2 times the length divided by a number. It could be 1, it could be 2, it could be 3. It's the number of antinodes, the number of these bulges. So here the wavelength is 120 centimeters. Here, this is where n is equal to 1. This is where n is equal to 2. There's 2 antinodes. So this is 60 centimeters. Here there are 3, 1, 2, 3 antinodes. So it's 120 divided by 3, 40 centimeters. And this is how, like the strings on a guitar, work. They have certain frequencies that cause standing waves. The sound you hear from a guitar is a sum of a whole bunch of these. And if you want to change the pitch, you change the length by putting your finger on the strings. Changing the length of the string, changing the natural frequency it oscillates at. When you make the string shorter, it goes to a shorter wavelength, which is a higher frequency. And here's a video showing standing waves. So these are standing waves generated in a string. As you can see, when it gets to the right frequency, you get a nice standing wave. There's nodes that don't move, and antinodes that move very fast. But if you change the frequency, you'll see a different number of nodes and antinodes. This is 1, 2, 3, 4, 5, 6. Oh, we're just changing it. So this is unstable. Now here's 3, 1, 2, 3. And I think at the beginning it had 6. But yeah. You can also have, they don't have to just be one-dimensional like this. You also get standing waves on flat surfaces. So here, this is a Cialdini plate showing sand settles in the nodes when you put it on one of these plates, and as you vibrate it at different frequencies, you'll see different patterns. If you ever watch, The Rings of Power, the opening sequence with Amazon Prime, and the opening sequence with and here you see for different notes, you get different standing waves.
The first experiment for the cymatics music video is called a Chladni plate. Now, Chladni plate's basically a metal plate attached to the top of the speaker. There's sand on top of the plate, and you play different tones through the speaker. The plate vibrates, which forms different shapes depending on the frequency of the sound.
Well, we blew up a lot of speakers with the Chladni plate. So there was a lot of experimenting around the Chladni plate, primarily looking at how much volume we can put through there, how much sand to actually put on the plate, and the different shapes of plates and what different patterns would be created because of those shapes. But what we were really testing was what frequencies create the most interesting repeatable patterns, because that was a key point. So we ended up playing pretty much every audio frequency through the plate to see what different shapes it would form.
And for most frequencies, it doesn't really do much, but when it hits a frequency that resonates with the plate, it forms a really nice pure shape. So we found out what those tones were, and those were the tones we used to draw the plate in the video.
So they mentioned resonance. So it turns out if you excite something at the frequency it like to naturally vibrate at, so if an object has a natural frequency and you put energy in at that frequency, equal to one of the natural frequencies, you'll get what's called resonance. You'll build up energy and you get a really big signal. A common example of this is pushing someone on a swing. You push in tune with the actual frequency of the swing, the person will swing higher and higher. And if you do it out of frequency with the swing, offset from the swing, the person will slow down. So the periodic driving force, the push, needs to be going at a certain frequency to keep the swing going. And you can do this naturally if you like pumping on a swing. You can move your body with the natural resonance of the swing to keep it driving and build up more and more movement. But various things will resonate when exposed to their natural frequencies. So for example, if you have one tuning fork is struck, another tuning fork of the same frequency will also vibrate in resonance. And when you hit something, like like this speaker, if you just sort of whack it and expose it to a whole bunch of different frequencies, the frequency, the sound it makes is its natural resonance. And if you've ever seen the trick where someone sings loud enough to shatter a wine glass, that's a resonance effect. You're singing at the natural frequency of the wine glass, so the vibrations of the wine glass get bigger and bigger until it shatters. Here's an example of waves, audio waveforms expressed with fire in a tube with a trumpeter. So the trumpet makes sounds at its natural frequencies, but you see the different frequencies playing sounds different ways in this tube. Now, musical instruments use standing waves and resonance to create various tones. So the natural resonant frequencies of something like a bell are standing waves in that structure. Or like a woodwind instrument, that tube of air gets standing waves formed in it, and that's what creates sounds at various notes. So guitars, violins, and pianos all use standing waves on strings to produce tones. Stringed instruments are tuned by adjusting the tension of the strings. Changing the tension changes the speed of the waves along the length of the string, which, because you change the speed and the wavelength is fixed, because it's the actual length of the, based on the length of the string, that will change the frequency. So adjusting the tension will change the speed, which will adjust the frequency that the string vibrates at. And the body of the stringed instrument acts like a resonance cavity to amplify the sound, and it increases certain frequencies and decreases others, and it creates that nice tone that you hear. And then lastly, here is this nice video of all kinds of strange science and music combinations with sound.
The film you're about to see has no characters. If you spare a little of your imagination, it is a film to describe to you the effect of cymatic frequencies on matter. Everything owes its existence solely and completely to sound.
that's the end of chapter 6. Here are some of the important equations. Frequency is 1 over period. Speed is wavelength over period, or wavelength times frequency. And the speed of light is 3 times 10 to the 8th meters per second. And that is the end of chapter 6. I'm going to stop sharing.